Imagine standing at the edge of something so massive, so profoundly dense, that time itself, the very fabric through which all events unfold, begins to slow, to stretch, to bend towards silence. Now imagine that this thing sits at the heart of nearly every large galaxy we have ever observed, including our own. You have been orbiting it your entire life. Let us begin with a fact that is easy to say but difficult to truly absorb. At the center of the Milky Way, roughly 26,000 light-years from where you are sitting, there exists an object containing the mass of 4 million suns, compressed into a region of space no larger than the distance between our sun and the inner edge of our solar system. It does not burn. It does not shine in any ordinary sense. It does not explode outward with the fury of a star. Instead, it curves space-time so severely that beyond a certain boundary, a surface we call the event horizon, nothing, not light, not information, not the very concept of escape, can return to the universe outside. We call it a supermassive black hole. And understanding what it is, how it formed, what happens at its boundary and perhaps beyond it, this is not merely an exercise in exotic physics. It is an inquiry into the deepest structure of reality itself, into the nature of gravity, into whether space and time are fundamental or whether they are, as some physicists now suspect, emergent phenomena, patterns woven from something even more elemental. When we look at the center of our galaxy, we are not looking at a curiosity. We are looking at a laboratory that no human hand could ever construct, a place where general relativity, our best theory of gravity, is pushed to its absolute limits, where quantum mechanics, our best theory of the very small, must eventually enter the conversation, even though we do not yet have a complete theory that unites them. The center of every galaxy is where the universe shows us its deepest unresolved tension, and it is where some of the most consequential science of our time is being conducted. To understand what sits at the center of galaxies, we must first be precise about what a black hole is, because the popular imagination often distorts the picture in ways that make the truth seem less extraordinary than it actually is. A black hole is not a hole. It is not an absence. It is not a void in the way we typically use that word. A black hole is an object, a massive physical object. It has gravity. It has spin in most cases. It may have electric charge in principle. It warps space-time around it. And it has a boundary, the event horizon, which is not a physical surface you could touch, but rather a geometric boundary in space-time, a point of no return defined entirely by the geometry of curved space. Here's a thought experiment that physicists find useful. Imagine space-time as a river. Ordinarily, this river flows gently, slowly, in a direction we associate loosely with the passage of time. You can swim against this current. You can move through space freely. Light travels along this river at great speed. Now imagine approaching a waterfall. As you get closer, the current of the river accelerates. You can still swim against it, but you must work harder. Eventually, you reach a point where the current of space-time reaches the speed of light, as fast as light can travel. At that point, no matter how hard you try, you cannot move upstream. You cannot return. Everything flows toward the center. That point, where the current of space-time reaches the speed of light, is the event horizon. Anything that crosses it is carried, inevitably, toward the singularity at the center. Now, for stellar mass black holes, those formed when massive stars collapse at the end of their lives, the event horizon might be a few kilometers across. The tidal forces near such a horizon would be catastrophic for any human traveler. But supermassive black holes are different in a subtle and counterintuitive way. The supermassive black hole at the center of our galaxy, which we now call Sagittarius A*, has an event horizon spanning roughly 24 million kilometers. That sounds enormous, and in absolute terms, it is. But because the event horizon scales with mass, and because the tidal forces at the horizon depend on the gradient of gravity across your body rather than the raw strength of gravity itself, a traveler crossing the event horizon of a sufficiently large black hole would notice nothing special at the moment of crossing. Read that again, because it is genuinely strange. You could cross the event horizon of Sagittarius A asterisk and not immediately notice. No alarm, no visible boundary, no physical sensation marking the moment. The laws of physics inside the horizon are, locally, the same as outside it. You would still experience the same physics of a room or a spacecraft or a drifting body in space, but you had crossed a threshold from which there is no return. The universe outside the horizon would still exist, but it would be permanently beyond your reach. The next natural question is, how did something containing 4 million solar masses, or in the case of the black hole at the center of the galaxy M87, 6.5 billion solar masses, come to exist at the center of a galaxy? The honest answer is that we do not fully know, and that honesty is important. There are several compelling hypotheses, each supported by some evidence and challenged by others. The first is direct collapse. In the very early universe, enormous clouds of primordial gas, hydrogen and helium, the simplest elements, may have collapsed directly into massive objects without ever passing through a stellar phase. Under the right conditions, a cloud massive enough and dense enough might bypass the ordinary path of star formation and collapse immediately into what cosmologists call a direct collapse black hole. These would have been the seeds from which supermassive black holes later grew. The second path involves stellar evolution. The first generation of stars in the universe, known as population 3 stars, were likely far more massive than the stars we see today, because the early universe contained no heavy elements to regulate and limit stellar growth. When these enormous first stars burned through their fuel and collapsed, they left behind black holes significantly more massive than those formed from stars today. Over billions of years, through mergers and accretion, the process of sweeping up surrounding gas and matter, these black holes could have grown to supermassive scales. The third hypothesis involves runaway mergers in dense stellar clusters. In regions of extraordinarily high stellar density in the early universe, stars may have collided and merged repeatedly, growing into a single supermassive star that then collapsed into a seed black hole of several thousand solar masses. In reality, it is probable that all three mechanisms played some role, in different environments, at different epochs. The universe rarely operates through a single mechanism when several are available.
What we know with confidence is the observational picture. We have now mapped the orbits of stars near the center of our own galaxy with extraordinary precision. A group of astronomers, led by Andrea Ghez at UCLA and Reinhard Genzel in Germany, work for which they shared the Nobel Prize in Physics in 2020, tracked individual stars for over 2 decades as they swung around something invisible at the galactic center. The orbits were precise, they were coherent, and from those orbits, using nothing more than Newton's laws of gravity and their relativistic corrections, the mass and the compactness of the central object were determined beyond reasonable doubt. 4 million solar masses, occupying a region smaller than our solar system. Nothing in known physics other than a black hole can account for those numbers. And then in 2022, the Event Horizon Telescope collaboration, a global network of radio observatories working together as a single Earth-sized telescope, released the first image of Sagittarius Alpha itself. Not a drawing, not an artist's impression, an actual radio image captured by the coherent interference of signals from observatories on multiple continents, resolved to the scale of the event horizon. It showed a ring of glowing gas, heated to extreme temperatures as it swirls inward, with a dark central shadow, the silhouette of the event horizon itself cast against that incandescent background. We have seen it. Most of what we have discussed so far concerns the relatively quiescent state of galactic centers. Sagittarius Alpha, by cosmic standards, is calm. It accretes relatively little material, it does not produce dramatic jets or extraordinary luminosity at this point in its history, but this is not always the case. And when we look across the observable universe, when we look at distant galaxies whose light has traveled billions of years to reach us, and therefore whose images represent the universe as it was billions of years in the past, we see something spectacular. We see active galactic nuclei. When a supermassive black hole accretes large amounts of gas, when material falls toward it rapidly enough, a structure forms called an accretion disk. This is not a simple ring of matter falling straight inward. It is a rotating, flattened structure of plasma, heated by friction and compression to temperatures of millions of degrees, emitting radiation across the entire electromagnetic spectrum. The innermost regions of this disk, where material completes its final spiraling descent, glow with extraordinary energy. Some of this energy is thermal. Some arises from powerful magnetic fields that thread through the plasma, twisting and amplifying as they are dragged by the rotating gas. And in many systems, these magnetic fields, organized by processes we do not yet fully understand, launch jets of plasma outward along the rotation axis of the black hole. These jets can travel at very close to the speed of light. They can extend for hundreds of thousands of light years, reaching far beyond the visible extent of the galaxy itself. When we observe the most powerful of these systems, the quasars, which are among the most luminous objects in the known universe, we are watching a single black hole, typically billions of solar masses, outshine the combined light of hundreds of billions of stars. A single object at the center of a galaxy emitting more energy than the entire galaxy surrounding it. The physics underlying this extraordinary luminosity is gravitational energy conversion. As material falls toward the event horizon, it loses gravitational potential energy. Some fraction of that energy, in highly efficient accretion systems, potentially more than 10% of the rest mass energy of the infalling material, is converted into radiation. Compare this to nuclear fusion, which converts less than 1% of rest mass energy into radiation, and which powers every star we have ever seen. A black hole accretion disk is, in this sense, the most energetically efficient large-scale process we know of in the universe. And those jets, those relativistic outflows, do not simply stream harmlessly into intergalactic space. They interact with the surrounding galaxy. They heat the gas that would otherwise fall inward and form new stars. They can suppress star formation across entire galactic volumes. They shape the evolution of galaxies over cosmic time. The black hole at the center is not merely a passive object at the bottom of a gravitational well. It is an active participant in the life of its host galaxy. There is growing evidence of a deep coevolution between supermassive black holes and the galaxies in which they reside, a relationship written across billions of years of cosmic history, evidenced by the remarkably tight correlations we observe between black hole mass and the properties of galactic bulges. The center shapes the whole. We have described the event horizon in geometric terms. Now let us dwell on it more carefully, because it is genuinely unlike anything else in nature. The event horizon is not a wall. It is not a surface in the ordinary sense. You cannot put your hand on it, and no local measurement could detect your crossing of it. Yet it is one of the most consequential boundaries in the universe, because information, once inside it, is, from the perspective of the outside universe, gone. This is the crux of what physicists call the black hole information paradox. In quantum mechanics, information is conserved. The complete description of a physical system at one moment determines its complete description at any future moment. This is a foundational principle, sometimes called unitarity, and it is deeply embedded in the mathematical structure of quantum theory. Information may change form, may become scrambled, may become practically inaccessible, but it is never destroyed. But general relativity seems to say that information falling into a black hole is lost to the outside universe forever. Sealed behind the event horizon, it cannot influence the exterior. And if the black hole eventually evaporates, as Stephen Hawking's remarkable theoretical work in 1974 suggested it must through a quantum mechanical process now called Hawking radiation, then the question becomes acute. Where does the information go? Hawking radiation arises from a subtle interaction between quantum mechanics and curved spacetime near the event horizon. In quantum mechanics of the vacuum, space is not truly empty. It is filled with pairs of virtual particles, momentarily flickering into existence and annihilating. Near the event horizon, geometry affects this process. One particle of a pair can fall inward while the other escapes outward, carrying away energy. To a distant observer, the black hole appears to slowly radiate, very faintly, at a temperature that depends on its mass. Over astronomically long timescales, far longer than the current age of the universe for a stellar mass black hole, and almost incomprehensibly longer for a supermassive one, the black hole loses mass and, eventually, in principle, disappears. If it disappears, and if the Hawking radiation carries no information about what fell in, as Hawking originally calculated, then the information is gone, destroyed. Unitarity is violated. But unitarity is one of the most secure pillars of quantum mechanics. This tension between general relativity's picture of the event horizon and quantum mechanics' insistence on information conservation is arguably the deepest unresolved problem at the intersection of fundamental physics. It has driven decades of theoretical work, from string theory to loop quantum gravity to recent conjectures about firewalls and entanglement structures near horizons. Most physicists today believe information is not truly destroyed, that the semi-classical picture breaks down in some subtle way, and that a complete quantum theory of gravity will reveal a mechanism by which information is encoded in the Hawking radiation, scrambled beyond any practical recovery, but preserved in principle. But we do not yet have that complete theory. The black hole sits at the intersection of our two greatest theories of nature, general relativity and quantum mechanics, and reveals with serene indifference that they are not yet fully reconciled. Here is where I want to pause and correct something. The popular conception of black holes is that they are cosmic vacuum cleaners, that they devour everything around them, that the galaxy is slowly being consumed by its central engine. This is not accurate, and the correction reveals something profound. A black hole, even a supermassive one, does not gravitationally dominate the galaxy around it. The mass of Sagittarius A, 4 million solar masses, is a small fraction of the total mass of the Milky Way, which contains several 100 billion stars, plus enormous quantities of dark matter. At the distances from the center where most stars reside, the gravity of the central black hole is negligible compared to the combined gravity of everything else in the galaxy. If our sun were somehow replaced by a black hole of equal mass, the planets would continue in their orbits undisturbed. Nothing would be sucked in. The black hole would be extraordinary at close range, but from a distance, gravity does not know what form the mass takes. Only proximity to the event horizon makes the black hole catastrophically dangerous in the popular sense. The galactic center influences the galaxy not primarily through gravitational consumption, but through energy output, through jets, through radiation, through the heating of surrounding gas during active phases of accretion. It is an influence of energy, not of gravitational reach. Furthermore, the night sky does not show us the universe as it is, it shows us the universe as it was. When we observe a quasar billions of light years away, we are seeing the universe when it was young, when galaxies were still assembling, when gas was plentiful, when black holes were actively growing.
Let us turn now to the most speculative, but still scientifically grounded, part of our discussion. What happens inside a black hole? General relativity gives a clear mathematical answer. Once matter crosses the event horizon, it is drawn toward the center, toward what the mathematics calls a singularity. At the singularity, the curvature of space-time becomes infinite. The density becomes infinite. The tidal forces become infinite. Infinite, meaning the equations break down, meaning general relativity as a theory reaches the limit of its own domain of validity. A singularity is not a place in space. It is, more precisely, a moment in time, a future moment that all infalling matter is directed toward inevitably. Once inside the event horizon, the singularity is not in front of you in space, it is in your future, and you cannot avoid your future. But physicists widely believe that the singularity is not physically real. It is a signal, a reliable signal, written into the mathematics of general relativity that the theory is incomplete. That at extreme enough densities and curvatures, quantum mechanical effects must intervene, must modify the structure of spacetime in ways that prevent the divergence to infinity.
What actually happens near the center, in the regime where quantum gravity effects would dominate, this we cannot say with confidence. We do not have the theory to compute it. The answer is genuinely unknown. Some approaches suggest that space-time itself breaks down into a discrete foam at the Planck scale, at length scales a billion times smaller than a proton. Some suggest that a bouncing cosmology occurs, in which the infalling matter transitions through a phase of extreme density and re-emerges, in some sense, on the other side. Some suggest the interior geometry is radically different from what the classical theory predicts once quantum corrections are applied. We are at the frontier here, and at frontiers, honesty requires acknowledging what we do not know. What we can say is this. The question of what happens at the center of a black hole, at the would-be singularity, is one of the central problems driving the search for a quantum theory of gravity. The answer, when we find it, will almost certainly reshape our understanding of space-time at its most fundamental level. Let us pull back now, far back. We have been describing physical objects and processes, black holes, accretion disks, jets, event horizons, but there is a larger pattern to observe. Nearly every large galaxy we have examined has a supermassive black hole at its center. The mass of that black hole correlates with the properties of the galactic bulge surrounding it, a relationship tight enough to suggest deep causal connection across the full span of galactic evolution. Galaxies and their central black holes appear to grow together, to regulate each other, through a feedback loop written across billions of years. This means that the conditions we see in galaxies today, the distribution of stars, the rate of star formation, the structure of the visible universe, bear the imprint of those central engines. The universe we inhabit was shaped, in part, by processes occurring at the centers of early galaxies, in the first few billion years after the Big Bang. Supermassive black holes are not peripheral to cosmic structure, they are embedded in it, they are participants in it. And the fact that we can now image them, that we can resolve the shadow of an event horizon across cosmological distances, represents one of the genuinely extraordinary achievements of observational science. The Event Horizon Telescope collaboration imaged the black hole at the center of M87, a galaxy 55 million light-years away, by synthesizing signals from radio observatories on multiple continents into an effective aperture the size of the Earth. The image confirmed the predictions of general relativity with remarkable precision. The shape of the shadow, the ring brightness asymmetry caused by the rotation of gas around the black hole, the structure of the emission, all consistent with the mathematics of curved spacetime that Einstein developed more than a century ago. A theory built on thought experiments and mathematical intuition, developed without any direct observation of a black hole, proved precise enough to describe the most extreme gravitational environments in the observable universe. This is the power of fundamental physics done carefully. Now I want to ask a question that sits not in physics alone, but at the boundary where physics meets meaning. You are made of atoms. Those atoms were forged in the cores of stars, in stellar furnaces that burned for millions of years before exploding and scattering their elements across space, seeding the molecular clouds from which new stars and planets formed, including the planet on which you stand. The galaxy that contains those stars, that contains the molecular clouds, the stellar nurseries, the planetary systems, the biospheres, is organized around a gravitational center. A massive, ancient, largely dormant black hole that was growing and shaping this galaxy when the solar system had not yet formed. Sagittarius A star is older than the Sun. It was present before the Earth existed. It will be present long after the Sun exhausts its fuel and the Earth is gone. And it sits there, at the center of the galaxy, curving space-time, marking the point around which hundreds of billions of stars orbit, including the one that gives us life. We are orbiting a black hole. Slowly, over the course of 225 million years, our solar system completes one circuit around the galactic center. In the roughly 4.5 billion years since the Earth formed, we have orbited the galactic center approximately 20 times. 20 galactic years. In all of that time, in all of those vast circuits through the galaxy, the central black hole has been there, constant, massive, geometrically reshaping the space through which we move, and we did not know it existed until recent decades. We could not see it directly until 2022. This is worth sitting with. The most massive object in our immediate cosmic neighborhood, the gravitational anchor of the galaxy, was invisible to us until we developed instruments sensitive enough to detect the shadows it casts in radio waves and the orbits it imposes on nearby stars. How much else is there in the universe that shapes our existence without our awareness? I want to close with a thought about what black holes are teaching us about the nature of space-time itself. General relativity treats space-time as a smooth, continuous fabric, a geometric entity that can be curved and stretched by mass and energy, and along the curves of which all motion occurs. This is a profoundly successful description. It passes every experimental test we have conducted with extraordinary precision, from the orbit of Mercury to the detection of gravitational waves from merging black holes to the image of Sagittarius A star itself. But the singularity at the center of a black hole and the singularity of the Big Bang suggest that this smooth fabric, this continuous geometry, cannot be the final description. It breaks down. It predicts infinities where physics should not permit them. This has led many physicists to suspect that space-time is not fundamental, that it is instead emergent, a large-scale description that arises from something more primitive. Just as temperature and pressure are useful descriptions of a gas, but arise from the deeper reality of moving molecules, space-time may be a useful description of something whose deeper nature involves quantum entanglement, or discrete structures at the Planck scale, or something we have not yet conceived. The holographic principle, the idea that the information content of a region of space-time can be fully encoded on its boundary, like a three-dimensional scene encoded in a two-dimensional hologram, emerged originally from the study of black hole thermodynamics. It has since become one of the most active and productive ideas in theoretical physics, suggesting deep connections between gravity and quantum information theory. The black hole, in this sense, is not merely an object to be catalogued, it is a window into the deep structure of physical law. Every time we probe it carefully, it reveals another layer of the puzzle. We began by asking what sits at the center of every galaxy. The answer, in one sense, is a supermassive black hole, a massive, spinning object that curves space-time severely, radiates almost nothing, occasionally devours gas and produces jets of extraordinary power, and shapes the evolution of the galaxy in which it resides. But the deeper answer is a question. A persistent, unresolved, extraordinarily productive question about the relationship between gravity and quantum mechanics, about the nature of information, about the structure of space-time at its most fundamental level. The universe has placed this question, this problem, this mystery at the center of every galaxy, as if to make certain we would eventually notice. We have traveled in this time together, from the orbit of stars around an invisible center to the moment a traveler crosses an event horizon into silence, to the image captured by a planet-sized telescope, to the deepest unresolved questions in theoretical physics. And I want to leave you not with a summary, but with a posture. There is a certain kind of awe that is not excitement, not the adrenaline of novelty, but something quieter. Something closer to what you feel standing at the edge of a very deep ocean at night, knowing that the darkness extends far beyond your sight, and that the darkness is full. That is what the galactic center offers if you receive it carefully. Not the thrill of the strange, but the gravity, in both senses, of the real. We live in a universe that is not obligated to be comprehensible to us. And yet, slowly, painstakingly, with instruments we built from metal and mathematics, we have extended our perception to the edge of black holes 55 million light-years away. We have seen the shadow of an event horizon. We have tracked stars in tight orbits around something that cannot be seen. We have detected the ripples in space-time from collisions of black holes a billion light-years